So, in the last lecture, we have derived mechanical energy balance for gas flow, which is G Z2 minus Z1, 1 minus rho A upon rho H plus D2 minus D1 upon rho H plus V2 bar square minus V1 bar square by 2 plus M minus M, that is equal to 0. Now, we will use this equation to illustrate some of the problem. So, let me write down the first problem. Say calculate air velocity, and flow rate of air leaking through an opening in a furnace wall. Given the following data are given: EF1 for contraction, that is equal to 0.5, EF2 for expansion, that is equal to 1, wall thickness that is equal to 0. Opening is a rectangular hole of cross section 0.1 meter into 0.15 meter. Now, for easiness, take friction factor. That is equal to 0.0064 and draft across the opening, that is equal to 1.5 millimeter of water. Density of air, that is equal to 1.17 kilogram per meter cube. So, normally furnace has opening, all of you know, and let us calculate the air velocity and hence flow rate of air. So, for the sake of doing the problem, you have to represent first of all in the pictorial form. Say for example, this is the wall of a furnace. This is the one, and this is the opening, and through the opening, say air is flowing. So, this opening is a rectangular cross section 0.1 into 0.15 meter, and we have to calculate the air velocity. So, as such, first we have to take, we will take, this is our plane 1, this is our plane 2. Now, apply the mechanical energy balance. Since it is horizontal, delta Z is equal to 0. Then there is no mechanical pump, so M will be equal to 0. V1, that is at the inlet and at the outlet 2, V1 equal to V2, since the gases are being exhausted in an environment. So, if we substitute all these things into our mechanical energy balance, then the equation that result is D2 minus d1 upon rho air, that is equal to F. That is what the equation result. So, what we have to calculate now? We know the draft across the opening, d2 minus d1 is given to us. Now, since this is minus F, now since the other end is open to atmosphere, so d2 equal to 0. So, we have d1 upon rho a, that is equal to F. So, we substitute the values in the proper dimension, and I will request you that you do yourself and replace F by, you know, is 2F L upon D E V bar square plus half EF1 V bar square plus half EF2 V bar square. So, now here, since it is a rectangular cross section, so you have to find out a D equivalent. So, find D equivalent, the formula I had already given, and then if you substitute all these values, then the answer V bar, that will come out to be equal to 3.98 meter per second, and air flow rate you can calculate, and air flow rate, that will come out to be 0.0597 meter cube per second. So, these are the answers for this particular problem. Now, here some of these steps I omitted. So, I request you to solve this problem. Now, d1 is given in millimeter water. So, you have to convert into Newton per meter square, and this conversion you do yourself and see that you come to this particular answer which I have given. Now, let us take another problem with respect to the design of the chimney and flue. Let us take, say, a brick flue. A brick flue must be designed to carry 425 meter cube per minute. The gas is given at 27 degrees Celsius and 1 atmospheric pressure of flue gas from furnace to stack. Furnace to stack. The flue will be horizontal. The flue will be horizontal with a total length of 100 meter. Total length of 100 meter, and has 4 sharp 90-degree bands. Here L by DE for each band is equal to 20. Also, the flue will be of rectangular cross section, with 2:1 ratio of height to width. the average temperature of flue gas, the average temperature of flue gas is 350 degrees Celsius. Now, what you have to calculate? Calculate the following. Calculate the following. A pressure drop, in millimeter of water to be expected if the flue were 120 centimeter into 60 centimeter cross section inside. B, energy consumed by friction. Energy consumed by friction. That is also you have to calculate. C, you have to calculate, say what would be the minimum cross section area, the minimum cross sectional dimension if the pressure drop were limited to 2.5 millimeter of water. So, this is a typical problem for say design of the flue and stack and so on. Now, there are something which is also given, and what is given is as follows. Say given molecular weight of flue gas, is 29. Then EF contraction 0.4, EF expansion 1.0, F is given 0.0037, viscosity in gram per centimeter per second can be calculated from this relation 19.3 into 10 to the power minus 7 T raised to the power 0.8, where T is in Kelvin and 1 Newton per meter square, that is equal to 0.02 millimeter of water. So, this is also given to us. Now, we have to find out first of all the pressure drop in millimeter of water to be expected if the flue were 120 centimeter into 60 meter inside. So, let us now straight away, since the design of the flue is not given, but it is said it has 4 sharp bends. So, the solution of the problem, we will have to first of all think how the flue is. So, probably the flue looks, say this is this could be the probable design of the flue. You have 1 band, 2 band, 3 band and 4 band. Somewhere here is the entry, somewhere here is the exit. this is my plane 1, this is my plane 2, and as such this is here expansion and this is here contraction. So EF1 contraction is given, EF2 expansion is given. So I will apply now. So this is the band 1, this is the band 2, this is the band 3, this is the band 4, and L by DE for each band is given to be equal to 20. So straight away we have to apply the mechanical energy balance, section 1 and 2. What we note, say since the fluid is horizontal, so Z1 is equal to Z2, V1 equal to V2, since the velocity are extremely small, there is no pump, so M is equal to 0. So if we substitute all these simplification into our mechanical energy balance, then we will be getting P1 minus P2 upon rho H, that will be equal to EF. And since we can substitute here EF, 2F L by D V bar square plus half EF contraction V bar square plus half EF expansion V bar square. Now remember here the L by D that will be equal to L by D of pipe plus L by D of all four bands. So first of all we have to calculate, because it's a rectangular cross section, how will you do it? So first you have to calculate. So here instead of D we will be putting DE, here also DE, so here also DE. So that is what we have to do it, and this is also here DE. So we will calculate first of all DE, you know already. So I am leaving some calculations for you. I am straight away writing DE will be equal to 80 centimeter. You know how to calculate? I believe you know how to calculate. So now we can calculate L upon DE, that is to be substituted, that will be equal to 100 upon 100 meter upon 0.8 meter plus 4 into 20. So L by D has become equal to 205. Now you have to calculate density at 350 degrees Celsius. I leave on you to calculate the density. I am straight away writing the answer. That will be 0.563 kilogram per meter cube. That is the density at 350. Similarly, we have to express Q. We have to express as 350 degrees Celsius, because it is given at 27 degrees Celsius. And from Q we have to calculate, say we have to calculate V bar. From Q we calculate V bar, and I request you to calculate V bar, and this value of V bar, that will come out to be equal to 20.42 meter per second. Now though I have given the friction factor, but then we can make use of the formula, as all of you know, that friction factor, that is equal to 0.0791 raised to the power Reynolds number to the power minus 0.25. So we can calculate the Reynolds number. You please do this exercise, calculate Reynolds number. That will be equal to dE V bar rho upon mu. Mu at 350 you calculate by the expression which I have given to you. I am leaving this exercise to you. Please do it. So Reynolds number, that will come out to be equal to 2.77 into 10 to the power 5, and if I substitute, then I get F is equal to 0.0034. Since all the values are known to me, now what I require, I have to substitute all the values into the equation P1 minus P2 upon rho, that is equal to EF. So, if I do that, then P1 minus P2, that is the pressure differential, 0.563 into 20.42 into 20.42, 2 into 0.0034 into 205 plus 0.2 plus 0.7. If you solve it, you will be getting 492 Newton per meter square, and that will be equal to 50.13 millimeter water, and that is also equal to 1.97 inches of water. So, this is the answer as required. Now, some of the places where I told you to calculate, please do the calculation and feel for the solution of the problem. Now, the second way to calculate energy consumed by friction. Energy consumed by friction. This you can calculate yourself, because in the mechanical energy balance, F is per unit of mass. So, if you multiply the value of F with the per unit of mass, you will directly get the energy consumed by the friction, and if I do that, then EF, that will be equal to 7.23 kilowatt. So, you have to appreciate that there is a considerable amount of energy is lost also in the to overcome the friction. It is very simple to calculate. All that you have to calculate EF, since EF is on per unit mass. So, multiply by the total mass and you will get the energy which is lost by the friction. Now, the next we have to calculate the certain pressure difference is given. So, we have to find out what is the minimum cross sectional dimension of the flue. Now, the same equation will be valid. Say we have P2 minus P1 upon rho, that is equal to V bar square 2F L upon dE plus 0.2 plus 0.5. Now, since here d is not known to us, since the cross sectional dimension is not known to us, so it is an unknown variable, and hence we cannot calculate V bar, also dE, as we were able to calculate in the previous problem. So, now let us see, now let height of the flue is h, then width as given, height to width ratio is half, width will be equal to h by 2. Now, we can calculate equivalent diameter dE, that will be equal to 2 into h by 2 divided by h plus h by 2. So, that will be equal to 2h upon 3. Now, since dE I know, I can also calculate the velocity in terms of h. You please do that. So, I am writing the straight away the equation. Say now I have say 24.5, because I have to convert the 2.5 millimeter of water into the Newton per meter square, divide by 0.563, that will be equal to 14.7 into 14.7, that is the flow rate, upon the cross sectional dimension h square by 2 square, 2 into 0.0791 or e to the power minus 0.25 into 100 upon 2h by 3 plus 0.7. So, this is my expression. Now, I can calculate Reynolds number also in terms of h. So Reynolds number will be equal to, you can calculate yourself, so Reynolds number will come 3.32 into 10 to the power 5 upon h. Now I know all the values. Now I substitute into the expression. So I will be getting a 43.52, that will be equal to 864.36 upon h to the power 4. I am simplifying and then I am writing. I request you to do the remaining exercise. 88 upon h to the power 0.75 plus 0.7. So I get an equation which is to be solved, that is equal to 854.5 upon h to the power 4.75 plus 605 upon h to the power 4, and that is equal to 43.52. Now this equation, you have one variable h which is unknown, so it can be solved by, this equation can be solved by the method of iteration, or you can also try a graphical solution. Now one of the important thing in case of solution of the problems pertaining to mechanical energy balance, one should also have a little bit mathematical background, because the solution of the equation, they end up either in the iteration or the graphical solution. So you should be able to also perform those type of methods to get the solution. Now in this particular case, you have to put several values of h or some guess value of h and see that right hand side equal to the left hand side. So I did something. So the value of h, that will be equal to 2.23 meter, and that of w, that is half of it, that is 1.115 meter. So that is the answer for the particular problem which we have given to you. So I give you one problem for self-assessment. Self-assessment problem. Try and see that you can do. And the problem is a brick chimney. A brick chimney 3.5 meter inside diameter, 3.5 meter inside diameter, let us say it is round, and 45 meter high, is to handle waste gases, at 330 degrees Celsius. The barometric pressure is 735 millimeter of mercury, and the outside air is at 27 degrees Celsius. Gases do not cool in passing through the chimney. In passing through the chimney. I will say this is the assumption. Now make the necessary calculation. Make the necessary calculation make the necessary calculation by plotting a draft at the bottom of a stack as ordinate and flow rate of waste gas as abscissa. Now, graph should cover complete range of flow rates. Complete range of flow rates from 0 to the value of flow rate at which the available draft is 0. The available draft is 0. That is, you have to cover the entire range. B, you have to calculate horsepower equivalent of the flow energy available for furnace draft at the bottom of the stack as the ordinate and flow rate of gas as abscissa. So this particular problem will tell you how much of the mechanical energy balance application you have understood, and this is straight away application of the mechanical energy balance, and to plot the result to see that how the draft is affected by the flow rate. So I will just give you the little bit hint to solve this particular problem. I will give you the answer, and rest of the solution you attempt yourself. So now in attempting the solution, first as usual, the vertical column, nothing to draw, 3.5 meter, height is given, temperature is given, and 45 meter is the height of the draft is given. So you have to apply the Bernoulli equation. So Bernoulli equation is G Z2 minus Z1 minus rho air upon rho flue into Z2 minus Z1 into G plus draft upon rho flue plus EF, that is equal to 0, or EF you can also write EF that is equal to F. They are the frictional force, it does not matter. So all that now in this expression everything is known, all that you have to put in proper units. So rho flue gas you have to calculate, rho air you have to calculate at the appropriate pressures. Then for example you calculate rho flue gas, that will come out 0.586 kilogram per meter cube. Calculate rho air 1.178 kilogram per meter cube. Now apply, write down into this balance equation. So I am writing straight away the equation that will be 445.97 minus EF, that is equal to draft upon rho flu. Now EF we have to take 2F L by D V bar square, since we are taking the section 1 and section 2 right at the inlet and right at the bottom. That is, in a way, what we are, this is our flue, this is my section 1 and this is my section 2. So that is where EF is equal to 2F L by D V bar square. So I can solve now for EF. F you have to calculate. F is already given, that is equal to, that is also you can take 3.23 into 10 to the power minus 5 kilogram meter upon second. So you can calculate now EF, that will be equal to 2 into 0.0455 rho flu into V bar into D upon mu power minus 0.2 into L by D into V bar square. So let us calculate F by the expression 0.0455 Reynolds number to the power minus 0.2. So if you substitute all these values, then the value of EF, that will come out to be equal to 2.17 into 10 to the power minus 3 Q raised to the power 1.8, because mind you, the value of Q V you cannot calculate because Q is not known to you. So Reynolds number has to be expressed in terms of Q. That's why you get. So if I write down now the expression, so then draft, that will be equal to 261.33 minus 1.27 into 10 to the power minus 3 Q to the power 1.8. So now I have to plot this value. So I put here draft, say in Newton per meter square, and put here Q. So at Q is equal to 0, the draft is 261.33. Now I have to take, when the draft is equal to 0, you have to put draft is equal to 0 and find out the value of Q. So Q will come out to be equal to 895.06 Q in meter cube per second. So something like this, that curve will go. So you have to see that how this curve runs here. Q will be in meter cube per second. So in the B part, you have to find out horsepower equivalent. So all that you have to multiply draft into Q, which is the flow rate, that is equal to 261.33 minus 1.27 into 10 to the power minus 3 Q raised to the power 1.8 into Q. So we have to find out, because this equation shows there is a maximum. So I have to take it the partial differentiation, that is dH. If this value is equal to H, horsepower dH upon dQ, I do that. I do this differential and I put equal to 0, then I will be getting Q, that is equal to 505.195. That means if I plot here, say horsepower equivalent of energy, horsepower equivalent of energy in watt, right, then this will be 0, that I have to calculate the draft from here, and it will go this way and it will again come to equal to 0. So, this value is of Q, that is equal to 505.95, and this value is 895.06. So, what I mean, this particular problem you have to solve yourself and see that you arrive at this particular solution. Now, having done the application of mechanical energy balance, also we have seen the design of the stack, chimney, flue, venturi, orifice. Now, next important thing comes is the fluid flow in burner. That is the fluid flow in burner. Now, you know that in the combustion, the stages in combustion are, see, first is the mixing, say mixing of fuel and air. After mixing, then you have ignition, you have to ignite the fuel, then ignition followed by chemical reaction, and the last stage is disposal of products of combustion. Now, in these stages, ignition, chemical reaction and disposal, they are the very fast steps, and the slowest step in case of combustion is the mixing. So, you can write down that mixing is the slowest step in combustion, that is mixing of fuel and air in combustion. So, it is said if it is mixed, it is burned. So, mixing is very, very important. So, it is in this perspective, a burner is an important part of a furnace. So, a burner is a very important part of furnace, and it rather supplies required amount of air, supplies required amount of fuel and air, it creates condition for rapid mixing, of fuel and air, and third, it produces a flame, which transfers thermal energy to furnace oblique charge. So, you see, a burner is a very important component of the furnace. It does several jobs. It has to direct the flame where heat is required. So, the arrangement of burner is also important. Now, what are the types of flame? Types of flame. One is a premix flame. Now, in the premix flame, air and fuel, they are mixed in the burner, and a mixture of fuel and air, it discharges into the furnace. So, as such, this type of premixed burner or that produces premixed flame, that is very risky, because any time an ignition happens during the mixing, then the chances of explosion is very well there. So, premixed flame, they are in fact risky and can cause explosion. Because already required amount of air has been mixed. So, all that ignition is required, and once the mixture ignites, it will combust and it may lead to explosion also. So, once again, in the premixed flame or in the premixed burner, all amount of air is mixed before the fuel and air mixture is discharged into the furnace. The diffusion flame, another is the diffusion flame. In the diffusion flame, not all air is mixed with the fuel. A fraction of air is mixed with the fuel and it is discharged into the furnace, and rest amount of air is supplied into the furnace. So, in a diffusion burner or a burner based on the producing the diffusion flame, a fraction of the air is supplied with the fuel and rest air is supplied in the furnace. So, these diffusion flames, they are not risky or not, and most of the industrial furnaces, all industrial furnaces use burner that produces diffusion flame, produces diffusion flame. Now, the diffusion flames are long, yellow and quiet, and sometimes they have incomplete reaction. Incomplete reaction, as against the premixed flame, they are short, they are noisy, but the reactions are complete because all fuel and air have been mixed prior to discharge into the furnace. Whereas in diffusion flame, the air and fuel, they mix in the furnace. So, in a diffusion flame, or a burner designed for diffusion flame, a small amount of air, is mixed with the fuel, and this air is called primary air. This is called primary air. Balance air is supplied through channels or ducts. They could be at several locations, and as such, this balance air is called secondary air. Secondary air, or sometimes they are called tertiary air. So, note the essential difference between premix burner and diffusion burner is that of the amount of air that is mixed. In premix flame, all air is mixed, whereas in case of diffusion burner, only fraction of the air is mixed with the fuel and rest air is supplied into the furnace. So, in fact, in the diffusion flame, the mixing of fuel and air is very important, because this mixing of air and fuel will occur in the furnace, because the primary air that constitute around 30 to 40% of the total air, rest air you are supplying in the furnace. So, the air which is supplied in the furnace, it must be well mixed with the mixture of primary air plus fuel, then and then the combustion will occur. So, therefore, the mixing of air and fuel it influences flame stability, emissions in the sense whether the combustion is complete or incomplete. Accordingly, the incomplete combustion products of combustion will also be there, and thermal release profile. Thermal release profile. So, what I wanted to say from here, that in diffusion type of flame or the burner based on the diffusion flame, it is the mixing of secondary air with a mixture of primary air and fuel is very important, because you are not supplying all 100% air through the burner, you are supplying only 15 to 30% air with the fuel. So, it is the characteristic of the mixture of primary air plus fuel that is discharged from the burner into the furnace that will create the condition of mixing. So, in such, the mixing of air is determined by the momentum flow rate of the jet produced by the burner when a certain quantity of air and fuel it passes through the burner. So, if I can represent, say this is my burner, this is the center line. So, here I am passing a mixture of fuel plus air, and this is, as this fuel and air mixture is discharged through the burner, then a free jet is produced. In the free jet, this is called potential core. So, when this mixture passes, then in fact the jet of air and fuel is spreads. So, jet spreads due to entrainment of surrounding. That is, the diameter of the jet at any distance downstream the nozzle or downstream the burner, it increases. So, here is the entrainment of surrounding. This is the entrainment of surrounding. entrainment of surrounding. So, what we see from this, that when the mixture of fuel and air is discharged through the burner, a free jet is produced. The diameter of the jet increases, and accordingly the velocity of the jet axially as well as radially it decreases. That is, this is the axial direction and this is the radial direction. So, further details of this mixing process for diffusion burner, we will take them next.